Okay, I spent most of today being fascinated by vectors. So it started with gradients, which was again a hangover from that machine learning series, and I I I saw a few videos on gradients before, but today I think I was formally introduced to gradients, and it also happened because at the end of yesterday's session, I basically checked out some vector videos, vector visualization videos, and what it did was it introduced me to gradients and vector fields versus scalar fields. So spent most of today yesterday morning, because I finished the session like around 6 a.m. So up until 9 a.m. I saw most of the scalar versus vector field and how one is derived, and I think I continued that throughout the day. I think 4 to 6 p.m. and then 8 to 9 I checked out some vectors, and the idea now is quite clear to me, which is these are the things that I would cover in, I think, calculus 4, which is vector calculus, and these things are important in multivariate calculus. So this segment, one segment was learning about gradients, the other segment was learning about multivariate calculus, and this is where I realized that, well, my understanding or my knowledge about multivariate calculus was very limited, and I never could penetrate that gap with multivariate calculus. I did 1D calculus, and today was my opportunity to be introduced formally and with some rigor to multivariate calculus, 2D and 3D, etc. And been on that train throughout the day, and it culminated to this video, which is like, it talks about, I think, what does the second derivative actually do in math and physics. I think some of the problem areas for me to revise is basically I want to know more about dot products and cross products, and more on the fundamentals. Like, the thing that I want to know about dot and cross product is like the direction, not direction, yes, the direction element. Like, when is dot product of two things perpendicular or parallel? So it has to do with some amount of trig. So I wanted to learn that. And also another thing that perplexed me for the longest time is this one, series, Taylor series. So when I saw this thing, I immediately wanted to learn more about it, and I asked Google to basically explain what Taylor series is a way to represent a function as an infinite sum of terms calculated from the function's derivative at a single point. So we take a single point and we calculate derivative, and we explain the sequence, not sequence, but since it is a sum, explain the series as a version of polynomials. So that is what I understood. It allows us to approximate, so the word is approximating a function using its derivatives, and is particularly useful when dealing with functions that are difficult to work with. So difficult to work with functions probably are the transcendental functions, and I will showcase the way I got to know about the transcendental functions. So these functions, transcendental ones, are difficult to derive. So essentially, this Taylor series essentially provides a polynomial approximation of a function around a specific point. Core idea: the Taylor series expands a function into infinite sum of terms, and each involving a derivative of the function at a chosen point, often called center or expansion point. Okay, so this is the formula, and the formula is not properly clearly seen. What I'm going to do is I'm going to go into my own drawing on the man. Okay, so like a foolish chemist, I learned gradient videos mostly from him. He has a series. It's not a full-fledged series, but it does a fair amount of it does a fair job in like elaborating on the gradient stuff. So that's not the issue. The talking point starts here. What's the Taylor series? So it expands, like this was the notation that I tried to write. It expands elements into infinity and uses derivatives basically. So series, I like this is the notation that I used, a I n j, and n basically is a sequence. The word sequence matters. The correct notation is this one, is the sum of a times not a subscript n, and n is basically 1 to infinity. So what I learned is there are many types of series. There is like arithmetic series, where the change is like, what is an arithmetic series? So arithmetic series is probably a sequence of many numbers, and the change in the sequence is constant. So an arithmetic series would be 2 plus 4 plus 6 plus something. I think, do I write? No, I haven't written the arithmetic series, but we'll see that in the ChatGPT answer. And then there's like geometric series, and the constant idea here is that when this was like arithmetic series is an addition, the change is added. In geometric series, the change is multiplied. I attempted to like showcase that here, but I like failed. Any case, harmonic series is a natural number reciprocal. So like 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, etc., etc. And then there's like power series. So special case of a power series is a Taylor series, and power series is something that I couldn't have written the notation for because I'm kind of like weak in this area, in this particular zone. But it is worthwhile to understand that whereas we went from 1 to infinity in like series, like just the ordinary series definition, adding things up, in power series we go from n0 to infinity. So that is like the case. And it makes sense because here I think this is a power series. Yes, this is a power series. So it starts with um, n being 0, so the first term is not here, and then 1. No, if n is 0, then like a times n, right? So n would be 0, and 0 times x I think is 1. That's why like it's just a 0, a subscript 0. So that is the idea. And Taylor series is a special case for this. A subscript n, x times n, like x to the power n. Taylor series approximates functions using polynomials centered at a point. So this probably is the most crisp of the definitions. It approximates the function using polynomials centered at a point A. And the formal definition, like formal mathematical equation for which is like a function n equals 0 goes to infinity, and goes to infinity, and this is basically a derivative at point A. N is like the number that we're going to get for like which term are we calculating the derivative for, and n is basically same here. And if a is equal to 0, it's a Maclaurin series where a is a 0. And then the next concepts are convergence and divergence. So convergence series is series in which the sequence converges as we add more to the number. So for instance, the geometric series is a convergence series. We add from 1 to n, we add more to it. And I think the annuity maths and like most especially the prominent number is like compounding. So we compound for 1 period, 6 periods, like 1 period for yearly, and then like half that, then we like reduce that to 3 to the 12th, 3 by 12, and then we go smaller. We go from year to month to week to day to hours to second, and like lastly we settle for e to the power something, and that is basically the same rate as the daily rate. So basically it converges is the idea. And then there's the divergence series, which is like harmonic. They're like I should be checking out the video on, not video but the response from ChatGPT. But the idea here is that it oscillates, or it doesn't converge. And then there's like transcendental functions. We can see e to the power x follows the power series. So like e to the power 0 would be I'll have to take the derivative, not derivative, but the derivation of the thing. Wow, I cannot do this. Wow, nice. Then there's like sine x. What happens here is this sign oscillates, and in sine you only get the negative uh, inputs like 3, 5, 7, not negative but odd inputs, not even ones. Then we have cos. We start with 1, which is this is worthwhile to notice this formula or function, like this series, this breakdown of this series, like 1 plus x. Since it is 1, so it is for it probably started with what it's probably started with e times 0, and e0 probably is just 1. That's why we have it 1. We just have 1, and then we probably took a derivative, like oh wait, if we took a derivative, shouldn't how did we get this number? I think we will, oh wow, yeah, I can do this. Never had I didn't know that I can do this. We'll have to check out how the editing works here. Any case, the cos is 1 minus the sine oscillate as well, but we have the positive numbers, etc. And this probably was what? This was what? This was something, but I'm not remembering what this was. Probably a special case or something. But any case, this was, or this is the entirety of the notes that I took for this. What I'm going to do is I'm going to pause. I am going to see which one would be the better, which one is a better place to go from here. Okay, so what is a series? Better explanation and better way. I think a series is sum of terms of a square. It's worthwhile to think of a concept and then think like what is the immediate word that comes to your mind, and can you define it on paper. So a series is sum of the terms of a sequence. Is this this is basically the idea. And then the types of series, there is like arithmetic, geometric, harmonic, power series, Taylor series, etc. What is convergence and divergence? So this is how they are defined. Some real numbers, so it converges to some real number as things we add more elements to it. Examples: geometric series converges to 2. Harmonic series, something that doesn't converge, it diverges, gets infinitely large. What you care about convergence and divergence has some implication in approximating functions, so this term is quite useful, approximating functions. And then we present complex functions as sum of polynomials like Taylor series, and we use them in solving differential equations, singular processing, quantum mechanics, etc. And this is how it is summarized here. I'm not going to read all of it. Again, this is a Taylor series, and we have went through this. Why was Taylor series needed? To differentiate, integrate, and compute numerically. So approximating complicated functions, some functions like these ones cannot be expressed easily with algebraic operations. So by the way, what is the definition of transcendental functions? Transcendental functions transcend algebra. That's why they're called transcendental functions. Numerical calculations, before computers we had to do it manually with hands. That's where the like it's better if you can take a derivative and simplify the process as opposed to something else, but modern computers do it for you. Using differential equations when closed form solutions don't exist. This one would be interesting. Taylor series are key tools in solving differential equations, especially when closed form solutions do not exist. I'd probably look into it more. Physics and engineering, I don't want to go there. Then how do we derive Taylor series? We want a polynomial. This is probably, yes, this is the definition of a polynomial. Wait, then what did I write? We want a polynomial. Okay, we want this is a complex thing to read. Okay, I wanted to this leads to ak. Okay, so the series becomes, if f of x equals f a, and if derivative of a with respect to a x minus a and so on and so forth. This is Taylor series centered at a. Why use Taylor series and function for functions like this and that? I think with this one is quite easy to understand. Summary, etc, etc, it doesn't matter. So I asked what are algebraic operations. Did I ask that or did it define? It did define because I asked something else, and I'm really glad that it did, because if it didn't, I would be kind of lost. Are not algebraic makes the point that these are not algebraic. And historical problem, why did people compute sine x before calculators? How did people compute sine x before the calculators? In the 18th and 17th and 18th century, scientists like Newton, Euler, and Lagrange needed to compute values like this, and they didn't have calculators, so it was quite helpful when they came up with or figured out this way of doing things. Examples: approximating sine x, we just do this, and then we approximate sine x at this point, and then so we now have this formula, something that we looked into, and once we just insert the point, it gives you a number, and that is basically a good approximation, and it approximates better, I think, as we add more terms. So the latter term probably approximates better. What is a polynomial? Okay, so this is the definition of a polynomial: is an expression made by adding, subtracting, or multiplying constants and variables raised to whole number of powers. So this is the definition of a polynomial. It is worthwhile knowing, because I somehow don't know, or I know, but it seems to be kind of vexing at times. And a are coefficients because they're constant, right? Constant coefficients. They are constants. It's the variable. The higher power n is the degree of the polynomial. Not polynomials are this. Where polynomials important, we can easily differentiate and integrate them, used in physics and learning models, not learning models but engineering, to model motion, area, pressure, population, etc., used to approximate more complex functions, and that is like Taylor series. What are transcendental functions? These are transcendental functions. What is a Taylor series approximation? We have gone through this many times, and it basically describes the portion that I get. This portion is described here. Yes, this was the geometric series. A geometric series valid for x higher than 1 is 1 by 1 minus x, and this geometric series is 1 plus x square plus x1 is basically a 1, like x1. Here x was 0, that's why x is not present in the first term. So I think this one is really important to know, because it's going to come in handy later. And the last thing I think I need to speak from here is visual intuition. Why does Taylor approximation look like? What does Taylor approximation look like? Let's say you want to approximate sine x near x equal to 0. The first degree approximate sine x, x accrued but works near 0. The third degree is this, better. The fifth degree, more accurate. As you add more terms, the polynomial hugs the sine wave closer and closer. So breakdown and what is the derivative? Part 1, derive the Taylor series for Euler to the power x from scratch. So step 1 is define the function. We did. Take derivatives. We did, and then all the derivatives. So all the derivatives are same, and it figures, because this is like it goes the same thing from integration to. Does it go from does it work the same way as we differentiate? It gives us like ex, becomes ex, but as we integrate, does it remain ex, or does it change? I think it remains the same, ex. probably a loan, but we are not going to look into that here currently. So plug into Taylor series formula. General form is this one. Since every derivative at 0 is 1, we get this one, this one, this one, this one. This is a full Maclaurin series for Ex. And I want to do practice problems later and see how this one works. We have JK Math, we have that professor, we have few other playlists bookmarked so that we can know how to apply this in real time. And I think Professor Leonard would be of great use as well in doing practical in-class problems using the first three terms. So approximate e to the power 0.2 using the first three terms. So number the first term we know, we don't have to, if we know the series, if we know the series, it just becomes a matter of like input the number. But if we don't know the series, we might have to derive the series. So this is the key thing. So we do this, and for the first three terms, we know the first term is 1, the second term is an x, and the third term is basically a derivative form, and this is a derivative form, right? X to the power x, or just it should be derivative probably for other functions, but since it's already it's ex, so all you get is just x square, I guess, something like that. So I guess the derivation mattered, and like if there's like professional people talking about it, for instance, there's like Harvard playlist. If I ever get to watch those, probably they break this down into more detail, but I think for my working knowledge this works. So the accurate value is this, and this is it for the ChatGPT aspect for thus far. Just one last thing that I would want to put out is, so this is basically the, if I want to check out the detailed version of this thing like CDs, I think this is a good place to start. It is the playlist, contains 193 videos, and like 131 starts with series. I think like around 60 there's like polynomials. So if I wanted to like refresh my memory on that, jog my memory on that, it's doable. 31, 32 is Taylor and Maclaurin series. 33 is hyperbolic functions definition identities, not related to series, three-dimensional coordinates and stuff like that. Introduction to vectors and their operation, dot product, linear algebra system. So okay, understanding matrices and matrix notation. Evaluating the determinant of a matrix, the vector cross product, inverse matrix and their properties, understanding vectors, linear, etc. The Gram-Schmidt process, I don't know any of these. Image and kernel, linear transformation through vector spaces, basis and dimension, linear independence. So these are like new topics alien to me. Vector fields, divergence and curl, and this is like a hobby horse that I want to ride, and I want to get to this position where I know properly like what is a vector field and what is a divergence, curl, etc. I think if my understanding is correct, divergence and curls are like different types of vector fields, I guess. So more on those later. Green's theorem, evaluating surface integral difference, divergence theorem, introduction to differential equation. Differential equation would also be a nice partial differentiation. Yes, we're doing partial differentiation. It probably would be applicable in calculus 3, and might even be applicable in calculus 4, which is vector calculus as well. So classification differential equations, introduction to differential equation, I know these two things at the very least. Separable first order differential equation, linear first order differential equation, exact first order differential, homogeneous differential equation, linear second order differential, linear second order differentiation. What is second order differentiation? It's like I think it talks about gradient, like the area and the direction, not area but the magnitude and the direction aspect of it. Okay, power series solution part 1. So this would be interesting to see what this one talks about. Power series solution part 2. the Frobenius or Frobenius method and Leibniz-Maclaurin method. Okay, and the last chapter is systems of different equations, differential equations part 1. So I think once I completely watch through all this, I might have a better handle on just what to read, not what to read. Like I might have a better handle on calculus in general, because I think I am on the verge and I'm verging on um, learning most things that is covered in HSC level calculus. So I think if I burn through the entire playlist and check out the other playlist as well, especially in the like a basic understanding of functions, that kind of stuff from Udemy and Unacademy, I think is a playlist as well. That kind of thing. I think the combination of all of this could make me very much competent in the basic level mathematics at least. uh, and then I can like move on to other stuff. For instance, I could get into the direct application of calculus. I can try some linear algebra, which is probably the right move, and based on that I think I can focus on one particular domain. I think statistics would be the right place to go. But in any case, I have rambled on for a long time now. I'm going to pause and see where to go from here. Okay, so this video is talking about Richard Feynman's average on a ball concept. So apparently something about not looking outside. All you have to know is what is the mass of the ball, and like what is what is something on the surface of the ball. What? Let me recheck that. If you want to know what is the potential here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. So all you have to know is what is the potential on what is the potential on the surface. Okay, and apparently we're going to be described throughout the course of the video on that particular thing. Let's watch. And if it wasn't obvious, we are here to learn about what the second derivative actually does in math and physics. It shows up in multitude of domains, areas, Schrodinger's equation, and whatever this equation is, and we are going to bear witness today. The video asks us to have a bare minimum understanding of Taylor series, because we should be using this idea, this concept of expanding a function as such. So this is why I took the trouble, and it is a very pleasant one, I might add, to learn more about Taylor series and bookmark what we should learn next in our mathematical conquest. It's promoting Harvard Quantum Initiative HQI blog. So yeah, I have this thing. I want to like be connected with different things, different uh, quirky stuff, like they them running their own blog. They probably have their own community, so I can follow those things on X, and like it shows up, all the latest and useful stuff shows up on my feed. So that is my biggest like uh, pet peeve, right? I want my social feeds to like reflect the happenings of the world. It doesn't happen. I mean, it doesn't happen, but it doesn't happen as perfectly as I want. Like there's so many people pulling, not pulling, but doing so many things at a particular time. But most of the time, I think the YouTube or Facebook algorithm maximizes for whichever is the most trending or hot button issue, and especially YouTube knows my preference. So if I'm like leaning heavy into mathematics for a while, it's going to show me different mathematical videos. So it does a fair amount of it does a fair job. Fair amount, not amount, it does a fairly decent job is the right phrase. And this video is not that old, it's only a year old. April 14, 2024. What was I doing April 2024 14th? This would be Poila Boishak. And what was I doing? I have no idea, no memory of this particular day. Okay, so it starts by defining, or not defining, recapping first derivative. So the idea is that two things are related. So x is anything. I think best way to conceptualize this is x is a random variable, and this function is a function of that random variable. So there is a relationship. There is like one-to-one relationship. This thing and this thing. This thing, although it is known as y, is just a function of x. That's why we use the phrase function of x. So once we start moving x from this point to this point, something happens here as well. The function moves a certain direction, and intuitively this is what we like intuitively know as derivative. So it's happening with respect to x naught. X is a function, if x, no, x is a random variable, and f of x is the function f naught. This tiny, should be supposedly tiny change is what the entire process is centering or focusing on. Like what, like instantaneous is the word that gets thrown around, not thrown around, but used, appropriately used. So instantaneous is the word I should be using as well. And then the natural question emerges, like what does the second derivative tell you? And rate of change of the first derivative is what the second derivative tells us, or tells me at least. Although I think this person quantum, I'm forgetting, I cannot see the entire name of the YouTube channel, but regardless of that, the idea here is that the second derivative to me is personal, because I wanted to create a filter for my data analysis. So I wanted to see like how much the stock is changing for a particular from day 1 to day 2, and like from day 2 to day 3, and what was also the rate of changing. So it was like first thing, the first date was like what is the rate of change for one stock, and the second thing was what was the rate of change of the first one. So this is like two things, and I think this video is going to challenge that way of seeing things, seeing the second derivative, and is going to add heightened insight into the thing. Let's see. And he rejects the interpretation that I just gave, or I've been using, in a very challenging, like not challenging, but a very appropriate way. Appropriate. I need to find. I need to expand the horizon of my vocabulary, right? Vocabulary, vocabulary is the right way. So it doesn't. This person doesn't want to know what it tells us about the first derivative. It wants to know what does it tell us about the function itself, the original function itself, which is, I think, commendable way of going about it. Okay, what this slide shows is that this is like the is this the structure, is this the motion of the ball in like 2 dimension, who knows. But the idea here is that we are going to compare here uh, f of x naught directly with the 2 points like dx and dx this side, the dx that side, and we're going to take an average, which is like this this notation indicates an average minus the actual number to see like something. Okay, so he this video did the math that I dislike, so it like expanded the original formula into some form of Taylor expansion, and that's where we get the half number and like this and that. And the idea here is that it expands both ways and some of the terms cross out, leaving us with, and we also take a limit as dx approaches 0, and we will see that in the graph to visualize it more accurately. So this is what we are left with. It basically tells us that something about the point at which the function is and the points around it, the average points around it, and the intuitive idea is something that I can relate personally, because we've seen this happen. Like, we've seen this image in where? We've seen this image in uh, business 235, I think, where we take the second derivative and it has to do with curvature. And as you can see, this point, these 2 points around the main f naught, fx naught, are higher and should be on average bigger than this one, and as a result it shows curvature in this regard. Like, it is like, if the number the difference between these two average minus subtracting this one is higher than 0, then the curvature is concave up, is the idea. And also concave down anytime, and I think I'm going to read from here. And if a function is concave down, then at any point the values of the function around that point are on average lower than the limit are on average lower, so the limit is negative. I don't know why limit is negative. Okay, sure, why not. And then we get a negative second derivative, so this whole average on a ball business. Okay, we are going to see also what is the what is the second derivative of a second derivative or something else? Yes, this one. What is the curvature of a straight line 0, which explains why the first order terms in the Taylor expansions cancel out. Okay. And then the next natural progression. What if we expanded the concept in 3 dimension? Oh no. And it has some multivariable calculus implications, which is even worse. So the 3 dimensional version of it is, we are going to have a circle and we are going to take tiny portions of dx, I think, and we are going to compare points around that sphere, and that would be the 3 dimensional equivalent of what we already know to be the case, or know to be true. And this is the corresponding expression. Second derivative in 3 dimensions is written using the symbol here, which is called Laplacian. Okay, so this is the Laplacian. And why is there a 6? Why is there a 6? Do we get how would we get 6 in the second derivative? If we had a existing 2 and we had 3 dimensions, we get 6. Or if we had an existing 3, which we didn't, I don't see how else we could have gotten 6 here. And the intuition was correct, and that number is always 2 times the number of dimensions you're in. And this looks familiar, only because I know it's taking the derivative. Why are derivatives like x squared? Because this is like in the second, this is the second derivative, and that's why the superscripts are x squares with respect to x, plus with respect to y, plus with respect to z. These are in a vector field. I think it might be a scalar field because I didn't see a symbol here, but he might be like being parsimonious with his time. That could explain it as well. But in any case, okay, this link takes us here, which is the derivation of how the second how the 6 came about, I guess. Yes, how the 6 came about, number 6. Does it look like anything that I would be able to understand, comprehend? Absolutely not. Absolutely not. No. Waves on a drum head. Waves of a drum head. Acknowledgements. So this is this is quite a lot. I'm not going to understand any of this, so why bother? Okay, this is interesting because this takes me back to electricity and circuits, stuff like that, thermodynamics, stuff like that. Okay, current and electricity, stuff like that. So the idea here is, for instance, for example, we say say we have some electrical charge distribution defined by a function rho of x. So this is rho of x, some electrical charge distribution emanating from it, I guess. How would we come up with the equation for the potential energy function generated, like V, I guess, is the voltage. So potential energy function generated by this charge distribution. Although this seems like a tough problem. Okay, again, let's see what he has to say. Okay, so the idea here is that it requires work for me to like push this plus from this negative charge, because naturally they are attracted, and it generates higher vol potential, which is like voltage, the more distance it generates as a consequence of me acting on it. I don't know. And I think the better mind intuition is, when we lift something, it has more potential because there's such a thing called gravity. And gravity would, if we lose the thing, if we like stop exerting force to push it upwards from underneath, then the thing is going to fall and the thing is going to break, because they are an exactly harder to fall. We heard that. And likewise, the exact thing happens in reverse. So this one like naturally wants to get away, so as it goes away it loses potential. So this is talking about electromagnetism, something that I have zero clue about, so I'm just going to skip through this. Okay, and now he's getting into like deep rooted quantum stuff, which I'm not interested in. So I would comment on this thing though. The idea here is that once you have a what you have like a charge, if there's a negative charge and there's a point outside something, and if the velocity is positive compared to this one, this there probably exists a negative sign, and we can like, if I ever crave to know about more electromagnetism stuff, I think we should return here and see. And that's where the equation, yes, this one, like 1 divided by epsilon or something. And last thing he was talking about, assume a position wave function of a particle looks simplification, something about probability and Gaussian. Okay, I'll just like, for the sake, because it mentioned Gauss, so I'm just going to check this one out before I get into my next venture, which should be this one, by the way. It's using the second derivative knowledge of, okay, this one is on top, and the average of these 2 points would be lower than this one, so the number sitting at top is higher, just higher, and so high that it's going to really over my head. Okay, so I think there's some silver lining in sticking through this video, which is it talks about two things. First, it talks about wave functions, and like how, remember how waves behave like particles and stuff like that. Like, some was it wave or something else? I think it was it probably was light. Does light behave like this? What behaves like, say, a wave and a particle simultaneously? Okay, whatever the case is. So this is like the wave thing, but there's also a like, because of Heisenberg uncertainty principle, two things cannot have. If we know the magnitude or momentum, we cannot know the position, and if we know, and vice versa, know the position, cannot know the magnitude, because it would be like in motion, something like that. So it takes somewhat of a Gaussian distribution. It goes from this and then like spreads out, something like this. I don't know. And this like the kinetic energy, it also includes the kinetic energy, because kinetic energy basically means like momentum. So I think kinetic energy might as well be some precursor precursor to momentum. And okay, just I'm going to stick 1 more minute and then we're done. Jesus. So I was kind of doing Schrodinger's second equation. Holy shit! Holy shit! There is indeed a physicist career opportunity available for me. It seems. If I like, if I can follow through a quantum physics video with zero skill and zero knowledge about anything. So why not? Why should I not pursue it in the future, in like 5 to 10 years time? Okay, so this video gets into what I was trying to get is like the first derivative of x squared. This curve is just 2x, and the slopes are getting from negative numbers to positive number, and it's getting smaller. Here there's like the rate of change for the slope, which is like the first derivative, is absolutely zero. So the rate of change is steep here, but in a negative direction, zero, and then like highest slope, highest slope. So that is the relationship, much more clear. Talks about the second derivative, which is like concave down. The y value is going to be lower than that because it's like the slope is higher than zero, and then like lower. So when the second derivative is higher than 0, and when basically x is greater than 0 as well, which happens in the case of positive slopes, the shape we get is the typical square shape, which is like concave up. And if the second derivative is lower than 0 and smaller than 0, not lower than, I think it's the right terminology, and the slope is negative, then it means that it is concave down, like this. Also, point of inflection when the second derivative is 0 is called the point of inflection. The minimum and maximum. So this is the maximum, and it basically tells you that this function has reached its maximum peak and cannot go any further. So only place to go is going down. And this is probably a maximum because the second derivative is positive and the first derivative is 0. So at both this minimum and maximum points, the first derivative is 0, and second derivative here is higher than 0, and this point lower than 0. That's how we know maximum and minimums. So the third derivative being 0 is called a jerk. I didn't know. The second derivative being 0 is basically the inflection point. The first derivative being 0 could be a minimum, could be a maximum, and we'll have to see if the second derivative is higher than 0. Second derivative being higher than 0 basically tells you that it's like maximum point, tip top, and the function can only take values lower than this. So there's the concave down, and the second derivative is higher than 0. It tells you that it is the minimum and the function can only go up, so the shape is concave up. Okay, I have two videos that talk about Taylor series. One is this, and the other one is 3 blue 1 brown. And what this video is doing is dealing with linear approximation, which is like turning the curve. I suppose that the ex curve might naturally look like this. I think it does. And like you take the slope, which is basically the linear approximation technique, and you take the first derivative, second derivative, not second derivative, the first derivative, which is basically the slope, and it gives you value 1. So that's how you approximate it. And it tells us that quadratic approximation is a better thing than linear approximation, and it kind of makes sense from a statistical point of view as well, because you have more variables to account for the same phenomena. So much more like quadratic probably takes in more than just one random variable, explanatory variable, that is. And as a result, we have second derivatives here as well, which by the way for e to the power x, just 1 1 1. And also it tells us that this would be the thing, 1 plus x plus x square by 2, and it accounts for why the 2 would be there to account for the, like if we took a derivative it give us a 2, so that is why we have a 2 here. I'm not entirely I my understanding is not clear, but it just says here. I'm going to take its word for it, take the word from Morphoclone. And it makes a case that if the quadratic is better than the cubic one, it'd be a better version, so it'd be a quadratic, not quadratic, but the one with 4 and then like one with 6, and the graphs basically oscillate from this one to this one. As you can see, the graph changes as you add more elements. There's also this idea about convergence, so at this point the values probably converge from both sides, and this is just showcasing how like we would plug in the number and get an approximated value. So it takes issue with the fact that the entirety of the curve was established from this point forward, x equals to 0, and that gave us the mathematical equation, or the series, basically the mathematical series from this particular point, and that seems sus. And the idea is that it only took information from its local region or something about locality. So the local region would be this thing, just like as x tends to 0, or not x tends to 0, but x is 0. So if the function is just like this and we took information like from this particular region, the function would still say the same thing, and the Taylor series would say the same thing, even though I have like totally distorted the function everywhere else except this one particular like region, green region. And he makes the case for why Taylor function probably has some flaws with respect to this is a piecewise function. Basically the idea here is that at 0 Taylor series basically says 0, but Taylor series should be giving us this value when x is like higher than 0, so the value from this side doesn't match the Taylor series value that we get. So I'm really confused about this particular thing. So the hypothesis is that functions that equal the Taylor expansions are the exception, not the rule. So the core argument here is that function like e to the power of x, sine x, or cos x are exceptions, not the rule. So I think he basically outlines that the key takeaway is that these functions that they converge and match their Taylor function value is kind of a miracle. So it talks about Taylor theorem and something about remainders, something about expansion paths and local information, etc., which I do not understand in the least. It probably is showing why we get the series as we get, because like from this to our function e to the power t, so this is like the distinction, not distinction, but why like our this particular function of e to the power x converges. And even though I do not understand, it gives us a reason why the Taylor series converges at at x0 equal to 0 when like we have this function e to the power x. I do not understand, but it apparently makes a guess. So in future, if I want to like understand for real how this works, this is the place to come. And here's something that I would probably understand best, because the mechanics of coming to this position is totally goes over my head. But the idea here is that their higher order derivatives basically don't grow. So if you like change from 5 to 10, it would be like 1 0 0 1. So is true for sine and cos. Like if you change the higher order derivative like d to the power 10, 20, 100, is going to oscillate between 0 and 1, it doesn't grow, so it probably is stuck. So as you can see, it is stuck 0, negative 1, 0, etc. Which is the reverse case for piecewise function. This is the piecewise function, and see, like, as we take more derivative, it just goes into like absurd number. So this is also key for piece of information. So the functions that they that converge and like equal their Taylor function value are called analytical function, and these are like analytical functions. And the most of the functions that we would work in real life would be analytical functions, because they can be made out of other functions like this. So we take these functions and together we can like create composite functions that would still be based on analytical functions. So that is like explains the title smooth versus analytical function. And on the other hand, the counter is true, which is piecewise function is not an analytical function, but it is smooth, and just because it is smooth doesn't mean it is analytical. And apparently these type of functions would not appear in the complex field, because they have a slightly different way of calculating derivatives, I guess. So complex numbers would not take in non-analytical functions like the piecewise function mentioned prior. And it also tells us that a function in like the complex plane, if it has like one derivative, at that point it has like higher degree derivatives as well. And this is like they become smooth as well. They have a particular name, which is holomorphic, and probably holomorphic and analytical stuff go hand in hand, it seems. And holomorphic functions, okay, holomorphic stuff are like smooth and therefore analytical, is a deep-rooted issue in complex analysis versus real analysis. So here we have the intuition behind complex and real analysis as well, which is cool, neat. So what I'm not going to do is check out Taylor series from 3 blue 1 brown, although I think this does a better job at breaking it down, make it much more easier to understand.
For how good it
I think it is not as complex as this one, so I am going to watch it at a further time period, not now, maybe as a monthly reminder revision to check like my comprehension level of Taylor series from a month from now. So today is Friday 20th, maybe in July we will revisit this, but not now. Okay, here's what we are doing briefly. This is saved in the playlist, so are these things. So I'm just going to shut down the thing. And 3 blue 1 brown has like 6 videos in the differential equation playlist along with Professor Dave. I think we should like, it's worth watching, but not right now. And so does Khan Academy, by the way. Differential equations AP calculus, Khan Academy. Okay. And then we have this one just like watch later, not right now. Heisenberg, I'm not going to. Okay, this guy is going to talk, sure, why not. The key takeaway is I might give it a watch just to see if it interests me in like broader chemistry or physics, stuff like that, because just like Taylor series, it just might pique my interest, right? But for now it goes away. Okay, the last straw is I created a playlist, and I'm going to go through that and see how what I learned from those, right? And if those video demand a separate recording session, we will be back. I'll be back, but for now I'm kind of tired, my back hurts, and today's session was kind of meh. Underproductive is the word I'm thinking. So we'll just call it a day and finish at the 1 hour mark. So few more seconds. This was like the citations or the videos that I watched. This video, beauty in math. Let's see what they're doing. Okay, they're going to go on the tutorial route, it seems. Vector fields. Okay, enough for today.